18.4 is about acid-base titrations. Titrations are a technique for controlling the neutralization reactions drop by drop. The tools in which we use during a titration is either a burette, which has an uncertainty value of plus or minus 0.05 centimeters cubed, which is the most accurate device we tend to have to carry out a titration. Or you could do it by a simple burette or pipette and administer the titration drop by a pipette. A reaction will continue until what is called the equivalence point. This is the point of exact neutralization, where only salt and water are present. Depending, as we learned in 18.3, on the strong acid, strong base, weak acid, strong base, weak acid, or strong acid, weak base setups from 18.3, depending on that neutralization point, you may have some hydrolysis occur, and that will tell us the different pHs at the equivalence point. The equivalence point in a titration occurs when stoichiometrically equivalent amounts of acid and base have been reacted together. At this point, the solution contains only the products of the titration. Titrations are used in the process of standardization, which means we can calculate the exact concentration of one solution when the other is known. And so if we have a known solution of acid, we can titrate it with a base and determine how strong of a base we are working with through simple stoichiometry and molarity calculations. Due to probe wear and pH meters, we're able to represent graphically what's going on during a titration, and these are called titration curves. These are plotted values during the titration of change in pH throughout the titration. It is not linear, because remember, we are working with pH, and therefore we do expect more of an exponential graph. There will be 4 different graphs in which we look at. The first one we're looking at is a strong acid, strong base. If we take HCl and NaOH, we create NaCl and H2O. Because we have a strong acid and we have a strong base, we have no hydrolysis occurring, as we learned in 18.3. Therefore, the pH at the equivalence point should be 7. Below you will see a titration curve. On the x-axis, you have the volume, usually of the base. We can see an opposite curve of when a base is added to an acid, so the bottom part would be an acid, and so on and so forth. So this could be a flipped graph where the curve would be opposite of what we see here, so on and so forth. The same points still occur, it would just be in the opposite direction. All right, so there are a few points here that we need to see. Point number 1, the initial pH. This one, you can see the initial pH is at 1.0. That signifies we have a strong acid. That initial pH could also give us our pKa if needed. Sorry. Step 2. The pH only changes gradually as we're starting to titrate. So we are slowly adding our acid to our base, we're starting to add our base to our acid, and you're going to see a gradual increase, but it's not a large increase. It's until it hits what's called the point of inflection. At step 3, there's a sharp jump. This is called the point of inflection. And with a strong acid, strong base, you can see that the pH range of that point of inflection is from 3 to 7. So if we were going to choose a buffer for this particular reaction, we would need one around the 3 range and around the 11 range, as we saw back in 18.2. Step number 4, after the equivalence point, the curve flattens out at a high value. Again, we can see that it flattens out at roughly 13 pH, which signifies we have a strong base. And then step 5, that is our equivalence point. The equivalence point is the point halfway up the inflection. Because we know it's between 3 and 11 for the inflection, we now know that the pH at equivalence would therefore be 7. Now we're going to look at a weak acid strong base. So we're taking acetic acid and reacting it with NaOH to create a salt of that weak acid and strong base and water. Because we are reacting a weak acid with a strong base, we are creating that salt. We now have what's called anion hydrolysis, as we had talked about previously. Due to that strong salt, we are going to get a pH at the equivalence above 7. As you can notice from the graph, the initial pH is fairly high, which signalizes we're working with a weak acid. So at this point, yes, 2 does not seem particularly high, but it's higher than 1. At point 2, the pH stays relatively constant. Even though you are working with a weak acid in a strong base situation, you'd expect a much sharper curve. But due to this salt hydrolysis that is occurring here, it creates a buffer region that then goes back and forth, and that is allowed by that hydrolysis. Therefore, it does level out the pH change that is occurring, even though we are working with extreme differences in our chemicals. Our point of inflection at this time is a jump in pH of, let's say, roughly 7 to 11. It's not as much of a jump because we're not working with both strong acids and strong bases. After the equivalence point, the curve is at a high value, which signifies we're working with the strong base. And the pH at the equivalence would be above 7. Now, depending on what you're reacting, then you'd be able to pinpoint it more exactly. So if you were to go halfway up this curve, and so we have where the curve flattens out at the point of inflection, halfway between there, it's going to be roughly around 9 point something. With a more accurate graph, you would have a better view of what it would be. Now, something that's unique about the weak acid and strong base, whether you are looking at the curve going up or the curve going down, is this half equivalence point. This half equivalence point is when we have that buffer region. It's where half of the acid has already reacted and half is salt. So we have half the amount of acid present and half of it has already turned into a salt. And that is what creates the buffer, as I had mentioned before. That being said, you could calculate your pKa at this point as well. So I'd mentioned you could calculate your pKa from the initial pH. Here you could also calculate your pKa. The equation which you look at is pH equals the pKa plus the log of your salt over acid. This is from 18.3 when we were looking at the salt hydrolysis. Or is it buffers? Oh, I'm sorry, back in buffers in 18.2. Because you're at half the amount of acid, half the salt and acid is the same number. Therefore, when you take the log of 1, it actually becomes 0, and your pH equals pKa. So upon reading on your graph, at the half equivalence point, where you have your 2, look at where that region is, you're able to identify the pKa and or the pH. So you can figure out the strength of the weak acid in which you're working with. If you have a strong acid and weak base, so HCl plus NH3 gives you NH4Cl. Due to a strong acid, weak base, you get cation hydrolysis, and this means your pH is going to be below 7 due to the strength of your acid. I'm sorry about the graph that it didn't come through clearly, but the information is roughly the same as we have talked about at this point. The initial pH is 1, which tells us that we're working with a strong acid. The pH stays relatively constant due to that buffering we had talked about in the previous slide. And so here we have a buffer region as well due to that hydrolysis and the salt that is formed. You have a jump in pH from 3 to 7, so significantly lower than previously, which shows you that you are working with a strong acid. And after the equivalence, the curve, when it plateaus, is at a fairly low pH, again, representing a strong acid, weak base. And that pH at equivalence is going to therefore be less than 7. And if you look over on the graph, it is right below 5 for this particular reaction that's being represented. A weak acid and weak base. Because you're working with a weak acid and weak base, look at the graph. It's really funky and different. It is very difficult to find the pH at the equivalence. So step 1, the initial pH is fairly high, representing working with a weak acid. The addition of a base causes the pH to steadily rise. Instead of having that buffering region, you see a continual rise. And it's very hard to find the distinct points. That being said, it is very hard to find that equivalence point because the pH change is a lot less sharp for a weak acid, weak base. And after that equivalence, you have a fairly low pH. You would not see a huge net change in pH either due to the high starting point of your weak acid and the low ending point due to the weak base. Keep in mind, as mentioned before, we could add an acid into the base and it'd just be the inverse graph. However, all the same rules apply. Instead of finding pKa, however, you would find your pKb and your pOH, so on and so forth, and do your calculations as needed that way as well.